Once again, let's start by solving our quiz. Okay, so this is what we have referred to as a physical pendulum, as opposed to, I guess, ideal pendulum of just a mass tied to a rope. This is something real. So I was asking, what's the oscillation frequency of a disk that's suspended from one end? Right, that's what we have to find out, and we are looking for small oscillations. Now the first thing, as you asked during the quiz, I need to know what's the moment of inertia of this object about the point of suspension, about this pivot point, right? So for that, I actually have one piece of information. I know that for a disk, moment of inertia around the center of mass for a homogeneous disk is mr square over 2. How do I find the moment of inertia around the pivot point, which is at the edge? Well, parallel axis theorem. This should be center of mass times m times the distance from center of mass to the edge is r squared, so it gives me 3/2 mr squared. Good. Then the next thing I actually need to do is assume that the diameter of my circle makes a small angle with the vertical. So I mean, I've actually taken from my disk from the equilibrium position to a small angle theta. Now I have mg. Mg is acting exactly at the center of mass. There is probably, well, there is a normal force which cancels that mg. So, but I'm not interested in the translational motion. I'm interested in the rotational motion here. So what do I need to do? I need to calculate the torque due to mg. What's the torque due to mg? It was r cross f, right? Torque is r cross f. So here I can say the distance, so that would be my r vector also. The magnitude of the r vector would be r. The magnitude of the force would be mg, and I need the angle between them, which is again theta, mg sine theta. Which way is that torque trying to turn my disk? Clockwise or counterclockwise? Clockwise. It's trying to restore the equilibrium, so I'd say it's clockwise. How about my theta angle? Theta angle is increasing counterclockwise. So now I can write torque equals I alpha. So torque, I'll just write r mg sine theta is I times d square theta dt square. But now, because they are in opposite directions, let me put a minus sign. Okay? Is there a differential equation that we can solve at this stage in Physics 101? Not yet. Okay, we need to go back to our one and only differential equation, right? So it's going to be r times mg times, and if the differential equation is in this form, then I can solve it. But how do I get from the first differential equation to the second differential equation? It only works within the harmonic approximation if, as a radian, theta is much less than 1. Okay, if theta is much less than 1, sine theta was equal to theta. Okay, so this differential equation is approximately true. But in practice, we've already talked last time that it works really well. Okay, so now I can plug in everything. I is 3/2 mr squared I'm really worried about the projector today. So let's write that R G theta is 3/2 m r square d square theta d theta square. M's cancel, 1 power of r cancels, so d square theta d t square is minus 2/3 g over r theta. That's the differential equation that I can solve. I know that if I see this differential equation, the solution is going to be C1 cosine omega t plus C2 sine omega t. And if I take two derivatives, sine and cosine are very simple functions. I'll just get minus omega square from each one of them, and then the function itself again. So now I can plug that back in. I can see that minus omega square theta of t is minus 2/3 g over r theta of t. Theta is cancelled, minus is cancelled. So I was asked to find the frequency of small oscillations. I found it to be square root of 3/2 gr. Did I reach my goal? No? Okay. So I need to go to frequency. I asked the frequency of oscillations. You're right. This is angular frequency. New frequency was? This is angular, so I need to divide it by an angle. So it's going to be 1 over 2 pi 2/3 g over r. So now I reached my goal. How about units? G is, what should be the unit of frequency? Hertz, which is 1 over seconds, right? Which is equal to square root of G is meters per second square, R is meters. So units also check. Now, limits. I can look at, not so easy. There are no really informative limits here. If G is going to 0, there is no gravity. I would not expect any oscillation. Omega should go to 0. That sort of makes sense. But otherwise, there is really no easy way to check this coefficients 2/3. You really have to be careful during the calculation. All right. Let me ask you other question. I'll not answer it. That's if you want a challenge for you. If I take this disk, if I actually pivot it exactly from center of mass, then it's not going to do any oscillations, right? If I do the pivot from the center of mass, my omega is going to be 0. If I pivot it from the edge, we found omega is 2/3 g over r. So the question is, where along this line is omega maximum? Okay, so where should you actually put your needle so that you have the fastest oscillation frequency? Sorry? Yes, so what we actually need to do is solve this for a general D and then take a derivative with respect to D. It's not hard, but I always found the result is interesting. So, okay, it's not hard. You should play around with it. We have other methods to discuss today, right? And that is concerning more realistic picture of oscillations. Now, one thing you remember from our simple mass on a spring model was that my oscillations kept on going forever, right? The energy of the system, total energy of the system, never actually decayed. Why? Because these oscillations were just conversion of kinetic energy into potential energy and back. There was no source of dissipation. Now, practically any kind of oscillator you set up will have some dissipation mechanism in there. Right? If you actually do this experiment, you'll see that you can let the system go, it's going to make many oscillations, but if you leave your oscillator, go have lunch and come back, you'll see that at least the amplitude has diminished. Right? So let's try to understand what happens if there is, well, let's not call it friction, let's be more general. What happens if there is dissipation of energy in the system? So let me start with the same model. Some mass and spring. Let's even put it on some surface. I'm going to make the surface frictionless. But let's say this is in some fluid, like air. Okay. So let's assume that there is some air, or let's say fluid friction to our system. Okay. Now we would like to understand what kind of motion this oscillator does with such a friction. How did fluid friction behave if a mass was going with velocity v? It actually experienced a drag force Fd, and we said in general this is a very complicated process. Okay, it depends on what kind of fluid you have, whether there is viscosity in the fluid, whether it depends on the temperature of the fluid. But let's use the simplest possible model. Okay, we're trying to understand the basics here. The simplest model was just, as a vector, Fd was some constant. I'm going to call it B today. Okay, I previously called it gamma, I think. B times V. Okay, so the larger velocity you have, the more friction force you're going to see. In general, that's only true for low velocities, or if your fluid is very viscous. If you're trying to move within honey, you're trying to swim within honey, that's a good description. There are all sorts of other forces because honey is also sticky, but nonetheless, that's the force. So let's try to write down Newton's equations. Okay, if my spring is stretched by x of t, and let's say it's going right with velocity v of t. What are the forces acting on it? There is the air friction, and then there is the force of the spring, right? I said that the force due to the spring, now I'm in 1D, so I'm dropping the vector signs. Force of the spring is minus k times x of t, and the drag force is going to be minus b times v of t. So F equals F total, F net, which is the spring force plus the drag force, is equal to m times a and m times a is d square x dt square is equal to minus k times x of t minus b times dx over dt. So now I have a new differential equation, and it's going to be a little bit more complicated. Why is it more complicated? Because right now I'm looking for a function. When I take two derivatives, not only do I get back the function itself, but I also get the derivative of the function, right? So this is a harder differential equation to solve. Let me play around with it a little bit. So d square x dt square is going to be minus k over m x of t minus v over m dx dt. Now k over m, that was my oscillation, square root of that quantity was my oscillation frequency when there was no damping. Let me call it omega 0. And b over m is some measure of damping, how fast. If b is larger, I should be damping more, I'm dissipating more. So I'm going to call it gamma, okay? So let's try to solve this differential equation. Minus omega 0 x, you're right, this is omega 0 square x minus gamma dx. And here's the thing, you will learn methods of solving differential equations. The only way you can solve differential equations right now is so-called the method of inspection. So you basically look at it and concentrate for a moment, then suddenly it's revealed to you that what kind of function do we expect? We expect, if b is equal to 0, if gamma is equal to 0, we expect something like cosine omega t, okay? But if I just leave cosine omega t, it's actually going to oscillate forever. So I somehow must have solutions which are going to 0 at large times. So I'll actually I'll put in something which decays exponentially. So that part will give me the oscillations, and that part is going to give me the decay. Alright? I know that I'm not making sense at this point. Let me be more mathematically rigorous. I'm saying I am making up a solution. I'm saying this differential equation must be satisfied by such a solution. Right? So that's what I'll do. I'll just write that solution back. So let me say it this way. Let's try this solution. Okay, what's dx dt? If I take one derivative, I'll get minus omega sine omega t e to minus alpha t. But the derivative may be acting on the second term. I'll have minus alpha cosine omega t e to minus alpha t. How about the second derivative? Again, I might get the derivative on the first term, so I'll get cosine omega t e to minus alpha t. Or I may get the derivative hitting on the second term, alpha times omega sine omega t. Here, if I hit on the first term, it's basically twice the previous term, and the final term I'll have plus alpha square cosine omega t e to minus alpha t. Let's try to put this into our differential equation. What was our differential equation? Omega 0 squared x minus gamma dx dt. So the second derivative has two kinds of terms. I have minus omega squared plus alpha squared times cosine omega t e to minus alpha t plus 2 alpha omega sine omega t times e to minus alpha t minus omega 0 squared times cosine omega t e to minus alpha t. That was just x squared. And then what else did I have? Minus gamma times dx dt, which will be minus omega sine omega t e to minus alpha t minus alpha cosine omega t e to minus alpha. Now let me get my red pen and start cancelling things. First of all these exponential factors cancelled. They are the same in both terms. So what do I have on the left hand side? I have minus omega squared plus alpha squared cosine omega t plus 2 alpha omega sine omega t. And on the right hand side, what's the coefficient of cosine omega t? I find minus omega 0 squared plus gamma alpha cosine omega t is, how about the sine omega t, plus gamma omega sine omega. How can this equation be satisfied? Only if the coefficients of the sine and cosine are equal to each other. So minus omega squared plus alpha squared must be minus omega 0 t. That's gamma alpha. In the other part, alpha omega is gamma omega. Omega is cancelled. Oh, that's great. So I have alpha is gamma over 2. Now I can plug it back here. Minus omega squared plus alpha squared. So gamma squared over 4 is minus omega 0 squared plus gamma squared over 2. So omega squared is omega 0 squared minus gamma squared over 4. So what did I find? I'll find that x of t, there is some constant that has to be determined by my initial conditions, times cosine square root of omega 0 squared minus gamma squared over 4 times e to minus gamma over 2t. Okay. Now, what was gamma? Gamma was b over m. B was my drag coefficient. So, what kind of solution did I get? First of all, I still have an oscillating term. Oscillating term means that I'll have my cosine, but the amplitude of cosine is actually decreasing in time. Okay. So, you remember what an exponential looks like. It decays to 0, right? So that sort of gives me a bound of how much my cosine can oscillate. Okay. And then I have the oscillation of the cosine. Okay. So that's what a damped oscillator looks like. It actually oscillates. So the energy loss, the decay, is related to my damping. So that is given by e to minus gamma over 2 times t. So if gamma is 0, if drag is 0, I never get decay. I get back the old result. But there's also one more important thing. The oscillation period. So t is 2 pi over omega. So new omega is not same as old omega. My period has increased. Omega is omega 0 squared minus gamma squared over 4. So the period is larger. That's sort of what you expect. If you're moving in air, your oscillation should take more time. There is always drag on it. Okay? So that's what a damped oscillator looks like. What you can do is, you can also, I'm not going to do it, you can look at the energy of the oscillation as a function of time. You will see that this energy actually decays to 0 with e to minus gamma t. Okay? So your damping actually makes your energy, your mechanical energy, to be converted into heat, right? So that your mechanical energy decays with time. But here is something interesting. My new frequency, so new frequency, let me write it in terms of the original parameters. Omega squared was k over m, and gamma is b over m. What happens if I actually increase b more and more? Can I make this frequency go to 0? Of course, right? B is an independent parameter. If instead of doing my experiment in air, if I do it in water, B will be much larger. Even if that's not enough, what happens if I do it in honey? Okay? There's a lot of B. And here's the thing. So there are 3 kinds of damped oscillations. If k over m is larger than b squared over 4m squared, that is exactly what I described. You have a decaying but oscillating system. For historical reasons, such an oscillation is called underdamped. If, on the other hand, b square over 4m square is larger than k over m, then it's really interesting. Inside of the cosine became an imaginary number. What's the cosine of an imaginary number? What's the definition of cosine? E to I theta plus e to minus I theta divided by 2, right? So if I put in an imaginary number, the cosine of an imaginary number is cosine hyperbolic, sine hyperbolic, which is essentially again an exponential. So if really you have that case, you basically just have exponential decay. Okay, you go to 0 very quickly. There is so much damping in your system, you cannot oscillate at all. Okay, you just directly go to your equilibrium position. Such a system is called overdamped. And in the middle is when these two quantities are equal to each other. And then your solution is really interesting. You basically, what happened? Your frequency went to 0, which means your period, the time it takes for motion to repeat itself, went to infinity. So you make exactly one oscillation. Okay, and such a thing is called critically damped. Now, here's an example for you. I know most of you do not drive yet, but Bilkent has a lot of speed bumps. And in almost all cars, the tires are connected to the body via suspension. Okay, it's basically an oscillator. Now, what kind of an oscillator should we use? Should we make it overdamped? What happens if I make it overdamped? Overdamped means there is no point in using a spring there. It's basically not going to oscillate. That's like putting a metal bar there that sort of kills the idea of the suspension. If you go over a speed bump, you feel it, all of it, in your body. What happens if I actually use an underdamped spring? If I actually make it frictionless, then when I pass, the car will keep oscillating for the next, I don't know how many seconds, but you'll pass through the bump without any change, but you'll keep oscillating, which is so. Suspensions, actually, you go to a car mechanic. He says let's adjust the suspensions. What he's adjusting is that making those suspensions critically damped. Okay, you pass, you do not feel all of the bump in you, but you do not keep oscillating. You just make one oscillation. So that's where you try to adjust your suspensions to. For some reason, most of you are using, I would imagine, Bilkent buses to go to the city, and for some reason I noticed that the driver's seat, there is also a suspension there, and I don't know why, but they keep it underdamped. So I mean, you pass through the speed bump, and the driver keeps oscillating for the next 5 seconds. I don't know why. Some they seem to like that. Okay, but that's okay. So the important thing, I mean, you don't have to memorize these formulas. Know what dissipation can do. It can actually kill the full oscillation. It can make the system into an overdamped system. critically damped is important because it's just one oscillation, okay? And even when you don't want any loss, there is always some loss in your system, okay? So even the best oscillator you have, what are the best oscillators we have? Do you know? It's not tying a mass to a spring. How did we define why is an oscillator useful? What did people do with the pendulums first? They measured time, right? They used flux. So apparently, yes, you know the result. Why is the frequency depend? Why does the definition of time use the cesium atom? Because cesium atoms, well, atoms in general are the best oscillators we know of. Okay, we can measure their oscillations very precisely, and they decay very, very slowly in certain prepared states. Okay, so that's all I want to talk about oscillations. Next week, we have still one more week to go. I'll solve as many examples covering all the chapters we've done since the second midterm, and something related to also second midterm. So please show up for the lectures next week. We'll do a general review of what we have learned in Physics 101.